Welcome to this video on Lenz's law. In this video, our main objective is going to be to answer the question, what direction will the current flow? Now that's a very vague question to the actual full question, which is, what direction will the current flow when I induce a potential difference in a loop of wire? So if you haven't watched the 3 videos leading up to this one in the EM induction part of our magnetism series, you want to check that out. Otherwise, this will make absolutely no sense to you. So we want to first start by thinking about this idea. And the idea was that we could generate a potential difference, so we could generate voltage in a coil of wire if we change the magnetic flux in a certain amount of time. The faster we change it, the more potential difference. So how would we change the flux? Well, we could change one of several things. We could change the strength of the magnetic field. We could change the area of the loop of wire. Or we could change the angle between the magnetic field strength and the area. And the rate at which we change one of those things, we will generate X amount of potential difference. Now, of course, we know that potential difference is also equal to I times R. So if we think of R being the resistance of the wire and the potential difference being generated as delta V, I would be the value of the current that is established by changing these things. So that's the big question here, is what direction will the current flow when I change the flux, the magnetic flux? And this is known, the answer to that question is known as Lenz's law, and it's actually a very fundamental idea of conservation of energy, and you could even look at it some ways in terms of Newton's third law, and I think that's very interesting. So let's take a look here what we're going to be doing. So I have a loop of wire, and I have it in 2 different situations here, and then I also have a different perspective drawing. So here we're looking at it kind of on the side, here we're looking at it kind of from the top. This is the same loop. So I'm just doing it so that we can see different perspectives. Now what I'm going to do here is I'm going to push this magnet, this bar magnet, into the coil. And this is going to be a velocity vector here. I'm pushing this, I'm just showing that's what I'm going to do, and then I'm going to pull it back out again. And we saw from the simulator in the previous videos that that would generate the electricity in here. Okay, that would generate a current in this loop of wire. So out of the things that make up magnetic flux, the thing that I am changing in this is actually B, because I'm not changing the angle of A relative to the magnetic field. I'm not changing the area of this loop, and I'm going to do it at the same rate. So what I'm doing is by pushing it closer, I'm increasing the value of B, and as I pull it away, I'm decreasing the value of B. So I'm going to go ahead and write that out below here. So by moving this into the field, B will increase. Okay, so what I could write that as is the change in the magnetic field will be positive, and therefore the change in the magnetic flux, I'm going to say, is positive. So both will increase. Here, as I pull it out, B will decrease because I'm moving the source further away. So delta B, or the change in the magnetic field, will be negative, and here the change in the flux will be negative. Okay, so let's see what happens. When I first push this into this coil, B is going to increase. So what's going to happen is, and Lenz's law says, that the current will form in such a way as to prevent, so we want to be able to prevent a change in flux. Okay, so this is what's going to happen. In other words, when you push something, it opposes. So maybe the better word to use would be not prevent a change in flux, but oppose a change in flux. We want to oppose a change in the flux. Now, it's not that something's deciding to oppose the change in flux. It's a natural response, and that's something I really want to, make clear, is that this is a natural response. It's not a decision, okay? So we're looking at the result here, and then we're inadvertently explaining what's happening. So what we're seeing here is it's like as if you push, remember Newton's third law, if I push something, it pushes back on me with the same amount of force, but just in the opposite direction. So in other words, if I push a table, it can't magnify the force that I'm pushing with, and the table moves back at a greater acceleration than is proportionally possible to its mass. So it has to push back on me, and the fact that there's an opposition will provide the necessary reaction that we see occur. So when I put the bar magnet into the coil, there's an increase in the flux. And the result is that there's going to be an opposition in that change of flux. So let's look at what's happening here. Here's my magnetic field lines. Okay, these magnetic field lines, I'm just isolating little tiny portions of it just to make for less arrows. And what I'm seeing here is that the flux is increasing. So I'm going to draw kind of an arrow here to represent the flux. Okay, maybe it starts off small and it gets larger. Now to oppose that flux, what I'm going to need to do is generate a magnetic field in this direction to prevent the change. Because remember, if I have vectors, if I say I have this vector b1 and I want to add b2 to it, if b2 points in the opposite direction, then what will happen here, let me make b1 a little bit bigger, is that I'll end up with b1 in this direction, but it will be a little bit less than what it was, right? The b net, I should say. But let's say I want to prevent any sort of change. So if I have b1 pushing in this direction, and I add b2 pushing backwards, and they're exactly the same value, the net b is going to be 0. So that's what's essentially happening, is it's saying that you can't create any magnetic flux through this interaction. So in a way, it's a conservation of energy law. What it's saying is that by pushing the magnet into the coil, yes, you're doing work in this situation, but you can't gain more than the work you do. And so what it's saying then is that there's going to be this countermagnetic field formed, in this case, a counter field, to prevent the change. And if there's a countermagnetic field formed, then what that means in this case is if what we call the applied flux, so if I'm going to call this the applied magnetic flux, and then we're going to have the induced magnetic flux. The induced magnetic flux is going to point in the opposite direction than the applied flux, and that's going to cause a field that forms in the same direction as the flux, and that's going to cause a current that's going to go in this direction. And I'm going to show you how that's possible in a minute. So if I'm looking at it from the top here, what I'm seeing is the field is pointing this way, right, relative to the area vector. So we just flip the orientation a little bit here. And we say that because that's going to give a net increase, let me change the color here, in the magnetic field, thus flux, that the coil is going to make its own magnetic field, the induced flux and field, that has to oppose that change, okay, by natural responses to oppose that change, because it can't create anything extra than is there in the first place. So the work done in moving the magnet can't generate more than the work it put in terms of the energy. And the result is that what happens is I get this counterclockwise motion like this. Okay. We'll come back to that idea here in a second. Now let's go to this position where now I'm moving the magnet out of the loop. Okay, so what's happening here is that the magnetic field is still pointing in that direction, because notice the north end of the magnet is still in the same orientation. But what's happening now is that the flux or the field first. Let's look at this. So the applied field is decreasing. Okay, so it decreases, and therefore the flux, the magnetic flux, B here, is also decreasing. So again, Lenz's law says that the natural response will be that there's an opposition to a change in flux. So if it's decreasing, the coil is going to induce a flux. So here I'm going to call this the induced magnetic flux. That's going to point in the same direction now. Because if something is decreasing and you're trying to prevent it from decreasing, you're going to point your vector in the same direction as that vector. Because now, instead of subtracting the two vectors to 0, I want to make sure that they don't change. So I want to add them up. So as one's decreasing, I need to make the other one more so that it prevents this change. So what happens now is we see a clockwise, if we're looking from this side, we see that the direction of the current will actually flip. So when I look at it from here, remember, I have magnetic field lines still pointing in the same direction. The issue is that this net magnetic field is decreasing from the bar magnet. So now the coil is going to have a natural response that will prevent the change, and if the change is decreasing, I must point in the same direction to prevent that. And if I do that, if that happens, that means it needs to have a clockwise current, so the direction changes as that occurs. Now let's think about how the heck do we know what direction this happens in. Well, we're using that right-hand rule that we looked at way back in earlier videos. This is the right-hand rule for a current carrying wire. And the idea here is that if I think about my fingers as being the magnetic field, right, and my thumb as being the direction of the current, my fingers are going to be in the direction of the induced magnetic field. So everywhere in green here, where I've looked at this induced magnetic field and the induced flux, that's the one that responds to the applied flux, which is in the gold and the red. So when you have magnetic flux that's increasing, your induced flux will oppose. So if you put your fingers wrapped around this wire, they'd be wrapping around the inside of the coil, and your thumb would point in the direction that I've drawn the current. And you can wrap your hand, you can move your hand all the way around. Here, as the magnetic field is decreasing, or the flux is decreasing, the induced flux is going to point in a way to prevent or oppose the change. And so if you put your fingers down into the coil, you see your thumb points in the opposite direction. Here's an important thing to think about. We only care about the portion of the area on the inside of the coil. Your fingers on the inside matter, not the direction that they point on the outside.